Okay, thanks a lot, Miguel. Thanks a lot to all the organizers for the opportunity of you gave us to present our work in front of this nice audience. And yes, as you were saying, together with Alberta, we're going to tell you about quantum correction to Calabi-Yau black holes due to D0-branes. And this work is mainly based on a paper we put on the archive back in February, and also some work in progress we are currently doing together with Dieter Lust and Carmine Montella, a PhD student at Max Planck Institute. So let me start with a really brief summary of the whole presentation. So I'm going to anticipate a little bit also what Alberto is going to talk about. In the first part, mine, we're going to focus more on understanding how you can, these D0-brane corrections could affect BPS black holes. And in particular, from two points of view. First of all, how this may affect the way in which the deck scales. When I talk scales, I mean the scales that appear in the gravitational effective field theory that generate these black holes as solutions. And from the second point of view, more specifically, we're interested in understanding how these corrections can modify the way this black hole experience phase transitions. And presentation that take place at the level of the FT when we hit the scale appearing inside the higher derivative expansions. And in part one, we will mainly focus on a simple control example, a simple control setup with a four-dimensional black hole, BPS black hole, which uplift to a black string. Instead, in part two, the one of Alberto, we're trying to generalize all of these for generic Calabi-Yau black holes. And the most interesting finding we're gonna have is that there are non-perturbative corrections that appear only in the general case, which are somehow completely screened in the black string case. And part two will be devoted to try to give a physical interpretation to these corrections. Now, let's start with my presentation and let's start with the basics. So consider a theory of gravity, go to low energy. It can be well described by an effective field theory. Now you want to go beyond the leading order, you want to add quantum effects. This means that you want to add higher derivative corrections. The higher derivative corrections in general are made and built as operators containing higher order terms in curvature, and therefore by naive dimensional analysis must be suppressed by a certain mass scale. And the exact kind of mass scale that is going to appear essentially depends on the nature of the mechanisms that you use to produce these terms within the effective actions. You can have several kinds of scale that appear. An example of these is the quantum gravity scale that we can naively define as the scale at which an EFT description of a gravitational theory is not anymore available. But below the quantum gravity scale, we can also have other scales, which in general are associated with milder breakdowns of the effective field theory. And when I say milder breakdown, what I have in mind is essentially a Caruso-Klein scale and a scenario in which we have a Caruso-Klein compactification, in which essentially we take an higher dimensional theory, we compactify, we have this tower of massive states, we integrate them out, and then the typical mass scale of these states appear as the object which is suppressing the higher derivative terms. And so what happens when we hit this scale? Essentially what happens is that the lower dimensional EFT breaks down as a lower dimensional EFT, but still there is an EFT description because all degrees of freedom reorganize just in another EFT, just higher dimensional. So black holes knows about these scales. For instance, neutral black holes know about the KK scale in the form of Gregorian-Flaming stability, or minimal black hole knows about the quantum gravity scale in the form of the size of the minimal black hole themselves. And the question we were asking ourselves when we decided to start working together, and well, we tried to answer in our first paper together, is how this Kaluza-Klein scale is seen and experienced by BPS black holes, or in general by protected extended objects, which, are BPS and stable. BPS and stable. And the reason why we think that this might be interesting is that from one side, we know that from the effective field theory point of view, when you hit at the Caruso-Klein scale, at the level of the theory, there is a jump. You have a decompactification. The lower dimensional theory is not anymore working, and you have to move to an higher dimensional theory. But from the point of view of the black hole solutions, especially if you try to work with black hole solutions which have classical embedding, which is already there, already working in both the lower dimensional and higher dimensional theory, it could be that the correction you add might be well behaved at the transition regime, it might not feel the same jump that you can see in the effective field theory. And well, this is just a naive expectation, but like we expect that this could be the case thanks to all this protection to the stability of these type of solutions.
So sorry, Matteo, can I quickly ask?
Yeah, sure.
So what is an example of the phase transition that you're thinking? Usually when I look at observables, physical observables as I decompactify, they're typically smooth, so I don't see any kind of phase transition there.
Yeah, and just thinking literally at the compactification. So what I have in mind, it will be clearer shortly, but what I have in mind is essentially that if you start adding higher derivative terms, you can see as this an infinite series, and you have like perturbative expansion and perturbative parameter, which is controlling this expansion. And then when I hitting like this parameter to be order 1, I'm expecting this perturbative expansion to some degree breaks down. And that
you don't mean any kind of like really like phase transition where something is discontinuous
no.
or okay.
Yeah. What I mean when I talk about phase transition, I have in mind just a jump in, for example, with a decompactification. And maybe this can be help to clarify even more concretely what we are gonna do and what you have to have in the back of your mind whenever I'm gonna talk about during this talk. That what we have done is just considering for the n equals 2, the simplest stuff we can think about, BPS black hole within this theory in large volume approximations. And the kind of the compactification, the phase transition we want to try to explore is essentially the decompactification from 4D to 5D. Clearly, as Miguel was saying, I mean, from the effective field theory, you kind of jump, and yeah, it is not completely clear if like how this jump will affect the correction to black holes. That's what we are going to explore, and in particular, we are going to explore these looking at the black hole entropy of black hole solutions and introducing the quantum correction due to integration out of D0-branes, which are the only relevant one in the large volume approximation. From string theory point of view, what we're doing is just looking at the phase transition from type 2A in Calabi-Yau to M-theory in Calabi-Yau. And even to be even more clear, the picture you should have in your mind is that we are considering one parameter family of solutions. We're not considering a dynamical process. It's not a dynamical phase transition, but we have like one parameter family of black hole solutions, and in some region of this one parameter family, we want to have black hole solutions which are much larger, whose radius is much larger than the M-theory circle. In a certain part of this family of solution, the black hole radius must be much smaller than the M-theory circle. And there must be like a bulk in which the radius must be same order of the M-theory circle. This is more or less what we are trying to depict. We are looking to solution of the purely four-dimensional equal to theory, and we are trying to see what happens if we try to make the radius smaller in this one parameter family to reach the same size of the scale of the KK scale of the D0-branes, and then we go even beyond, trying to reaching a regime in which the solution well, naively should be described by a five-dimensional approximation. So this is the story I'm going to tell you about. So from now on, I'm going to try to be quantitative on this, giving you more details on how we do this and how we study this correction how the correction to the entropy of this kind of object behaves. And yeah, unless you have questions, this would be the plan for the presentation. Little bit of review of the framework we're working with. Then we're going straight to the main example. So these black holes that uplift the black string. A few comments on another black hole BPS black hole system, just to see what is special of the black string and what instead is not special. So it's general. And then a few remarks before leaving the stage to Alberto. So there are no questions, apparently, so I'm starting. So the framework we're working with is for the n equal 2. This is just the action that all of us, we all know. There is vector multiplex sector, hypermultiplex sector. During this our work, we are truncating the hypermultiplex sector, and we also only consider the vector multiplex sector. What I want you to remember is that the vector multiplex sector is completely specified, fixed by a function called prepotential. That in the second bullet is this curly f. Did you see that once you fix this prepotential, all the kinetic operator, the matrix appearing in the action are completely determined. Something you may not be so familiar with is the fact that beyond the derivative theory, this framework emit an infinite tower of BPS operators, which are higher ordering derivatives. On the left-hand side, you can see like these. You can see my pointer? Okay, perfect. The left-hand side, you can see the superspace representation, and the right-hand side, instead, we are just unpacking them, and so you're showing the components of the superfields. And about this whole tower, what is important for us is that when we embed this in string theory, this curly f of g, that in general could be generic holomorphic function, are fixed in terms of topological string theory amplitudes. And the second important thing is that all this information can be actually encoded and condensed in a simple object, which is called generalized prepotential. Why we call this generalized prepotential? Well, essentially because if we use the generalized prepotential, all the formulas related to the property we know and love about for dn equal to a true derivative are still valid. We just have to take the prepotential and replace it with the generalized prepotential. The structure then is going to be the same. So let me be more specific. We first, just a technical step, we rescale the usual scalar field that we use to parameterize the vector multiplet space, the modular space. We introduce a generalized black hole central charge that depends on this rescale scalar field and on this generalized prepotential, and then all looks really simple. The tractor mechanism is just the standard one, just with general prepotential and with these rescale scalars. P and Q are just magnetic and electric charges of the black hole. And the BPS black hole solution are still there, are still available, and their near-resonant geometry is completely fixed by the generalized central charge. That's one of the reasons why it is called generalized black hole central charge. And on top of this, we still have a really nice and simple entropy formula for these BPS black holes, where the generalized central charge still plays the role of the area term, and then we have an extra term, which is essentially plays the role of a deviation from the area law. The last piece of information I need to give you to describe the stuff we are working with is that, as I told you at the very beginning, we want to work in the large volume approximation in such a way that only relevant corrections are the one associated with D0s. To do this, for us, means essentially to pick an ansatz for the prepotential. This is the prepotential we're going to use. The first term is just a 3-level standard cubic piece that you also have for Calabi-Yau compactification in the two-derivative theory. Second one is the genus 1 term coming from dimensional reduction of the Riemann square term in 5 dimension. And the last term is the most important for us, and is essentially what this G term is what encodes all the D0-brane effects, and especially it is a term which encodes higher genus corrections. Because if we try to expand this as an asymptotic series, it has this form. We have a perturbable parameter, which is alpha. Alpha is defined here. Please remind this, it will be helpful for the future. Alpha is scaling as 1 over y0. And these G's, which looks like just powers, like labels of a power counting, are actually corresponding to to the effect of higher genus correction. So this G is actually corresponding to the genus effect we are putting inside. Also, all of this is written in string units, so it's not clear, but each one of these terms is also associated with a higher order in the higher derivative expansion of the effective field theory action. With this, the review is finished. So if you have questions, that's the best moment. Otherwise, we jump on the main example. Okay, let's go. So we said we want to study quantitatively phase transition. Well, how correction to the entropy behaves when we decompactify. So what we are going to do is we need to find a solution with a family of black holes we can use to study this thing. And to do so, we focus on the black holes with no D6 charge, so the D0 to D4 black holes. These are the solution to the Lacter equation, and this is the entropy of this family of black hole solution. This kappa is nothing but the triple intersection number of the Calabi-Yau, and this D, in case you're wondering, is just, again, up to the numerical factor, nothing but the triple intersection number of the Calabi-Yau. And okay, we have these configurations, but not all of them are fine because, as I told you, we want to work in the large volume approximations the way that D0-brane effects are the only one which matters. So what we have to do is check if we are indeed within this approximation or not. So what we do is looking at the volumes of the 2 cycles and the Calabi-Yau manifold volume, and we impose that they are large, and this is essentially equivalent to impose a hierarchy among charges. And what we notice is that not all choice of charges can produce a solution within the large volume approximation, but actually this quantity here can be fixed at will, and independently of its value, we always are within the large volume approximation. So we have essentially a one-parameter family of solutions governed by this ratio that, thanks to the mechanism, is telling us is just governed by the value of y0.
Matteo, sorry, just to
Yeah, sure.
clarify. So when you say, so these volumes are at the horizon, like the
Yes,
value
exactly.
that takes.
It's
So
at the
you
horizon
want
of
to
the black
stay
hole.
large volume approximation in the horizon, not asymptotically.
Yeah. We want
Or-
it to be there everywhere, but thanks to the monotonicity of the volumes, we just have to essentially focus on how they are at the horizon of the black hole.
But the volume, it changes as you go, as you approach the horizon, or it stays fixed?
Yeah, sure, it changed because the scalar field in general will, well, in the derivative case, you don't see that, but in general, scalar fields may run. For instance, the D0 mass asymptotically and at near horizon is not the same because the dilaton is running in these black hole solutions in general, and this implies that, well, we have non-trivial profiles in space-times.
But then
So-
it increases or decreases as you move away from the black hole?
It should decrease closer to the black hole.
And does not depend on the charges, whether it's electric or magnetic.
No, well, I mean, clearly, yeah, surely. I mean, you can just fix the asymptotic value of the scalar fields. These are kind of independent because of Traktor mechanism. And then what the physical charge of the black hole, what are fixing is the value of the scalar field at the horizon. So essentially with this asymptotic value of the scalar fields, you can play to fix them at will, such a way that you can have like the volumes you want. But then like really the volume we are interested in to have under control is the volume of the two cycles in the Calabi-Yau at the horizon of the black hole.
Okay, so what you check is that the volumes at the horizon remain large,
Exactly.
not asymptotically necessarily.
Exactly. This is really crucial because, yeah, indeed. Everything here is defined at the horizon. The entropy is defined at the horizon, the scalar fields are defined at the horizon, the Traktor mechanism, when we enforce it, is fixing quantity at a value at the horizon. So we have these with one parameter family of solutions, and then we just compute the quantum correction to these. These are the quantum corrected equation of motion. This is the known perturbative correction to the entropy of this class of solutions. And something I want to remind you is that this G, which essentially encodes the higher genus correction to these solutions, we were able to expand these to give an asymptotic expansion to describe these in the form of a asymptotic series, and the perturbative parameter governing this asymptotic series was alpha. But this alpha now, you may start seeing that it is a pretty common object that is appearing more and more times, because not only it was the expansion parameter of the controlling the higher genus corrections, but by definition is also 1 over y0. And this y0, let's go back of one slide, is the parameter which is allow us to move inside this one parameter family of solutions. And let me add just one last thing about this alpha. Actually, it's not just a random combination, it's a very nice physical interpretation because it can be related to the radius of the black hole we are considering and the M-theory circle fiber. So it's the radius among the black hole and the KK scale. So maybe all of this seems confusing, but let's summarize everything. We found a one parameter family of black hole solution. Every single black hole is within the large volume approximation, and we can move inside this one parameter family, changing the value of alpha, which is 1 over y0 at the horizon. Then alpha small means that the perturbative correction of the effective filter are suppressed. Alpha large, alpha order 1 means that we are at the essentially breakdown of the perturbative expansion, and alpha large means that we are completely away from the validity of the perturbative expansion. But on top of this, we also have a really nice interpretation about how the black hole looks like, because for alpha small, our black hole is much bigger than the M-theory circle. So it's a physical object which lives purely in 4 dimensions. For alpha order 1, our black hole is essentially is the radius, which is the same order of the empty recircle, again, at the horizon. And finally, for like alpha much bigger than 1, the black hole is much, much smaller than the recircle. And so it should be better described by an object living in 5 dimensions, and therefore like a black string object. Now, this is the picture you have in mind. This is the picture that I gave you before, but all of this is qualitative. And now the goal is make this quantitative. Can we prove that we start from a black hole for the n equals 2, and taking a decompactification limit means alpha much bigger than 1, we actually get a black string? Well, the answer is yes. And now we will show you how we show this quantitatively, computing correction to the entropy. So this is pretty technical. There are a lot of steps involved, computational steps involved. I'm trying to be as quick as possible on these. So the main idea, and just giving you some ideas of what we are doing. So what we have to do is taking the prepotential, the higher genus part of the prepotential, then rewrite it in using the Markov representation as the topological free energy. Now, with this topological free energy, you see that there is an integral part, a series, an overall series, and we want to massage it, to massage this a little bit to make it, well, to rewrite it in a nicer way. And among the steps one has to perform, there are like change of coordinates. We have to divide among positive and negative modes, and we have to deform the contour of integration along the complex plane and do some Poisson resummations. All of these, I don't want to give the details, but just to say that there is a precise computation, a heavy computational part in all of these, in all these steps. But the really important thing you have to bear in mind is that the result of all of these, especially of the formation of the contour integral on the complex plane, is that this piece of the potential boils down to two contributions. One is that can be written as a line integral and is perturbative in nature because it's perturbative in alpha, and one which is picking some pole contribution and is non-perturbative in nature because is well, non-perturbative in alpha. Explicitly, these are the formulas. This is the perturbative piece, and is the non-perturbative piece. And now, what is amazing here is that the non-perturbative piece is purely imaginary, and the perturbative piece is purely real. And this means that I've been super fast, so probably you haven't noticed, but let me remind you that what is entering the entropy is only the imaginary part of G, the imaginary part of the higher genus correction to the prepotential. And the higher genus correction to the prepotential are defined by this Schwinger integral, but there is an extra factor of phi. So all what is entering the entropy is actually the real part of the Schwinger integral. So the perturbative part is completely caught by the entropy, and the imaginary part is completely screened. So we have these poles, but the entropy is not seeing them. Nothing, the black string completely screening the effect of these poles. We have them, but they're not seen by any physical quantities in the black string. And now, if you want to focus on the perturbative piece instead, just to give you something about this function that might seem ugly, is still a series, well, one can prove that this is a monotonic function for large value of alpha, and is essentially going to 0 for alpha large. So it completely diluted in the limit that should correspond, according to our naive picture, to the decompactification of 5 dimensions. So so again, this is just complete agreement with the standard understanding that when we go from 4 to 5 dimensions, all the higher genus correction and the nice gamma curve alpha structure we have in 4 dimension is not present in 5D n equal 1. And now let's move to the main quantitative result of our work. We're putting everything together. This is the quantum corrected black hole entropy formula for these D0, D2, D4 BPS black holes, which are within the large volume approximation. This is taking into account exactly of all perturbative and non-perturbative effects due to D0, but non-perturbative effects, as I told you before, cancels out. But in principle, we are also taking time into account. And now to check the quantitatively that all the story I told you about is working, we take the alpha quantification limit, that should be the limit in which the perturbative correction explodes, and it should be the limit in which we should be decompactifying 5D. And if you take this limit, you perfectly recover the black string entropy. There is a perfect match with all the exact results in the literature that have been computed exactly in the context of 5D n equal 1 theory, just using the supersymmetry of BPS, of the BPS string. Well, I think this is pretty exciting because this is a really quantitative check of and precise check of what we've done, and just going to flash some comments because we don't have time to talk about it. But if you want to try to apply to this formula to small black holes, you cannot do that because there are some, well, it's against the assumption you used to derive it. But we can still ask about minimal black holes within this one parameter family, and what you see is that essentially for a minimal black hole, classical and quantum correction must compete to generate a minimal black hole. And again, this is like a quantitative way to support the species scale description in terms of black holes. Now, I'm gonna be super fast this because I'm running out of time. But just to say, what is general, what is not of the black string. So in the D0 system, you can see that alpha is still controlling the perturbative expansion, alpha still this interpretation of the ratio among radius, and the correction are still finite. Now the difference is that alpha is actually what enters really is the modulus of alpha, because alpha in the D0 system is a purely imaginary quantity. And the reason why it's becoming purely imaginary seems weird, but essentially there is a attractor mechanism that is telling us that alpha must be purely imaginary, because alpha is related, well, it's completely fixed by the attractor mechanism. And well, we will see in the talk of Alberto that alpha will have the same interpretation for generalized black holes, but its phase will be really important for this discussion. Now, for the D0, when you turn on the 6 charge, you cannot decompactify because there are topological abstraction in 5 dimensions. I will skip about this. Ask me if you are interested about this. And another thing that there are also no non-perturbative corrections here in the sample potential in the Schwinger integral. However, if in the black string case there were poles, but we were not seeing them in the entropy, in this case we don't see non-perturbative correction due to D0s, but we also don't have a pulse at all. So, just a really short remark. What we have done is the following. We took, for the n equal 2, we compute something purely in the 4D regime, so this D0 effects, we added to a quantity computed for black hole solution extracted from the attractor mechanism in 4D n equal 2, and then we took the decompactification limit. The 4D theory, in principle, is breaking down, at least its asymptotic expansion is completely breaking down, but actually resumming this correction, we're able to well, show that the entropy is not seeing any jump, any discontinuity, it's just behaving smoothly and it's finite during the whole three-phase transition. Then we've been able to the best of our knowledge, to show for the first time a quantitative gluing among 4D black holes with 5-dimensional black strings across the whole transition regime. And just let me just emphasize the 4th point of this list. We show, because it will be fundamental for the second part, we show that in these two cases, the D0, D2, D4, and D2, D6, there are no non-perturbed D0 effects, even if the way in which these two effects are absent is different, because in the D0, D2, D4, there are poles, but they're not seen, and the D2, D6, instead, there are no poles at all. And with this, can just say to tell you, enjoy part 2, the part of Alberto. And maybe I can stop sharing and leaving the
Yes,
floor to Alberto.
you need to stop sharing, yes.
Okay, sorry.
Then Alberto can share.
Maybe I can ask meanwhile, so I mean, sometimes these 4D black holes can correspond to other things in higher dimensions, or maybe you see them as other black branes in higher dimensions. I guess to see this, you need to consider more than only D0 corrections, or what?
Yeah, maybe I can answer this shortly while Alberto is preparing. And so the D2, D6 is not uplift to a black string. The D6 is uplift to a Taubnut geometry, which is not a black string, and the nearest geometry is actually a length space, a 3-sphere quotient by a ZP symmetry. And actually, the amount of D6 charge is telling you which is the P in the ZP quotient. So during the whole time I talk about black strings, but yeah, generic for D n equal to black hole don't correspond only to black strings. And Alberto is going to tell you about generic Calabi black holes. And then your second question about probably, I think you have in mind why we are always uplifting to black strings or object in 5D. I'm not sure if it's part of the presentation of Alberto, but I can just tell you that yes, this is a limitation of the assumption we are working with. If we want to move only with the vector multiplet space and work with the large volume approximation, and starting with black holes that have a classical horizon, if you put all together this condition, the only thing you can do is decompactify one dimension more. And these are the objects you are finding. If you don't have D6 charge, it's a black string. If you have D6 charge, you have a near horizon geometry, which is a length space, a three-sphere question by ZP. We are working on going beyond, but I think that maybe this may be clearer also after the presentation of Alberto.
Okay.
Okay, so let me check that everything's working. Do you see how it's moving, like the slides and so on? Yeah, perfect. So also, I guess the pointer, right? I don't know. Yeah. So let me first join Matteo as well in thanking the organizers for giving us a chance to present our work here. And as he was saying at the beginning of his talk, this seminar have been divided very naturally into two parts. In the first one, we were mainly concerned about how quantum perturbative corrections to thermodynamic observables, in particular of supersymmetric and therefore stable black holes, can know or detect about the presence of additional UV scales such as the KK scale. But along the way, we made several observations that we believe are important and therefore deserve some kind of attention. And particularly so in regarding the presence or absence of non-perturbative D0-brane effects. And this is the main topic of this second part. But before posing the exact question that we're going to try to address, let me just briefly review the highlights of Matteo's presentation that will be relevant for what it's going to follow. So if you remember, the piece of the prepotential that was able to detect the presence of this KK scale in a dual M theory perspective was the contribution from constant maps from the wall-sheet to the Calabi. So this, from the four-dimensional perspective, was arranged in a formal power series of corrections in terms of some parameter alpha, which is complex in nature, in principle completely determined by the attractor mechanism, but complex. And if we want to actually go beyond that and perform all these nice matches and so on, what we need is to rewrite this expression in terms of a Swinger one-loop integral representation, which is nothing but the Kumar-Buff computation, but in this case, restricted to the tower of D0-brane. So this is what one ends up with. And as you can see by staring at this formula, in principle, there are potential non-perturbative effects, which, as we are familiar with when thinking about Swinger computation and so on, they're related to the singularity structure of the integral. So in this case, with the hyperbolic sign. Now, the location and presence of this pose, as you can see, will depend crucially on the nature, the qualitative behavior of the expansion parameter. So which kind of phase exhibits and so on and so forth. And in this regard, the two solutions that were discussed by Matteo are rather special, right? For instance, the D0, D2, D4 black hole system, the one uplifting to the black string, exhibits a purely real parameter. So this means that the pose of this hyperbolic line completely lying along the imaginary axis. On the other hand, for the D2, D6, the fact that this is now purely imaginary means that this hyperbolic sign is converted into a sign, and therefore the poles are now lying completely along the real axis. So they're completely rotated by halves. And nevertheless, despite the fact that, as Matteo was more or less fleshing out, when you try to do this kind of computation more carefully, you divide it into, making the change of coordinates and dividing into positive and negative modes, deforming the control of one of those so as to be able to reason the others and so on and so forth. Despite the fact that you typically pick up some residues due to these non-perturbative effects, we observed that in both cases, there was no non-perturbative D0-brane effect at all in any of the black hole observables, including the entropy, the BPS quantum entropy. But the reasons were different, as Matteo was saying. So in the first case, for the black string, we did pick up the residues along the imaginary axis, but they turned out giving some purely real contribution to the prepotential, therefore was not entering into any of the the computations at all. So and actually this was crucial. This is something that we should highlight. It's crucial to be able to make the matching, because these non-perturbative effects are badly behaved for large alpha. They actually grow polynomially. This is actually crucial to make the matching work. On the other hand, for D2D6, what happens is that the fact that we now have this pose along the real axis allow us to deform the two kind of sets of contours towards the imaginary axis, and we are able to write down a simple line integral, which is well-behaved, convergent, and crucially exhibits no non-perturbative correction at all, to the prepotential even. So in the end, we observe that there's no such effects at all. And one may, at this point, one may ask is, well, whether this state of affairs will persist in the most general Calabi-Yau black hole system at large volume or not? Or is it rather some special property of these two systems? And to address this issue, we need at least three things. So the first thing, of course, is to know how to extend the computation of these non-perturbative corrections to the prepotential in general. So regardless of the value of this alpha parameter, its phase, and so on. The second, of course, we need to extend our results. We only computed the entropy, the quantum corrected entropy for the D2D6 and the D0, D2D4. We need the most general solution to be able to address this question. And finally, depending, of course, on which kind of answer we get, one may want to understand in simple physical terms, what we get, why we get what we get. In particular, if there was a simple explanation that we could have used to kind of guess the result. So this essentially, this wish list comprises my outline of the talk. So let's go through each of these in turn. And let's start with telling you how to compute the non-perturbative corrections in general. So Matteo explained more or less that how to compute those in a rather direct way. So essentially what you do, you start from Kumar-Bafa, you change coordinates, so you find two different sets of line integrals with different integration contours. And for each, say, negatively charged state, what you do, you deform the contour towards the other half of the real axis. This allows you to do the Poisson resummation, as Kumar and Bafa did. But along the way, you also pick some residue, right? There's actually an interesting and equivalent prescription that one can follow, which is it will be proved to be very useful in my discussion. So if instead of deforming each of these contours of the negatively charged poles, what you do is slightly deform each of these sets slightly away from the real axis and resum each of them independently, also adding the arc at infinity, one essentially arrives at an equivalent prescription, at least for the D0, D2, D4 example, that is much more compact and actually treats both kind of corrections, namely perturbative and non-perturbative, in a democratic way. Okay? I should say that this kind of representation was also derived independently by Jarrod and Eran, but actually even more general, because in their case, they argue that they find a formula that also includes the D0, D2 bound states. In our case, we're only caring about D0-branes because they give you the leading order quantum corrections at large volume. Okay. So why do I say that they are this treats both corrections democratically? Well, because by essentially using Cauchy theorem, you can retrieve either the perturbative computation by Kumar and Bafa by looking at this first piece, on the poles of this first piece, which are literally the integers. And again, focusing on the hyperbolic sign, you also recover the non-perturbative corrections, which for alpha real lie along the imaginary axis, as I was. Now, interestingly, this formula, as we show in the first paper, can be actually used to compute these corrections more general. So in particular, if you allow this expansion parameter to have some non-trivial phase, the theta alpha here, what you find is that the perturbative piece, again, still always lies along the real axis, but the non-perturbative poles are now rotated away from the imaginary axis by precisely this angle here. And as long as the real part of alpha is non-zero, so for every system except for the D2D6, actually, this prescription works perfectly well. You can show that it's completely equivalent to the direct computation that Matteo was fleshing out. And it gives you a non-perturbative contribution of this form, whereas you can see it depends, it's isomorphic, it depends on y0 only, and it includes a sum of polylogs. Okay, so it's not very important to keep in mind right now what is the precise form. The only thing is that with this, we are able to say or we achieve the first goal, right? We know how the computations, the non-perturbative computations to the general D0, D2, D4, D6 solution look like, at least due to this D0. Great. So let's go now into the second part. And let's try to obtain the general quantum corrected entropy formula for the most general BPS black hole, assuming, of course, it exists. So let me remind you that, as Matteo was stressing several times, we always focus in the large volume regime. So this means that our generalized perpotential, namely the starting guide from which we derive everything, essentially contains, three pieces. One is the tree-level cubic piece that we are all familiar with. Then there are also quantum corrections due to the genus 1 linear term and the higher genus corrections that come from GV by thinking about these D0-branes. And everything else that we're throwing away is due to it's exponentially suppressed and is due to Gaussian. Okay, so everything that I'm going to give you is derived from this perpotential. Now, after some algebra, some tedious algebra, one can show that the most general quantum corrected entropy of this D0, D2, D4, D6 system looks like this. So it's kind of a mess. It depends, of course, on things that we expect, the H charges of the black hole, the topological data of the Calabi-Yau, and also some variables, the x's, the xa's, and y0 that are solved in principle to be solved implicitly, meaning that they will be the solution that one will find for each specific Calabi-Yau and for each specific range of charges by solving these kind of two attractor-like equations. And let me stress that the fact that we can only give this implicitly is not, it's not something new or special of this system. It also happened for the other two. For instance, in the D0, D2, D4, so the black string, the fact that this function is very complicated, it prevents us from finding an analytic solution. So the only thing that we can hope for is to obtain some iterative solution. And on the other hand, even by thinking at the tree-level perpotential, if we think about other systems, the 2D6, for instance, typically we'll have to solve some quadratic system that may or may not have a solution. But as long as we have some solution, then the entropy form is captured by this kind of wild beast. Now, what we can do to actually get convinced that this is correct is, to the very least, try to take some limits. Let me see. Okay, now it got frozen. Okay, now I think okay, let me see. Yeah, now are you seeing again, right?
Yes.
I lost it for a moment. Okay.
Yes, it's
good. So we can take at least the three obvious limits that we can take are the following. So first of all, you can turn off all quantum corrections, but still left completely arbitrary the charges of the black hole. And what you end up with is exactly the solution that was found 30 years ago by Smakov. So with exact same attractor equations and so on and so forth, which, as I was stressing, also is an implicit equation. You have to solve some quadratic system. Another possibility is to still keep the quantum corrections, but specify to simpler set of charges and see whether we retrieve well-known results. And in particular, what we can do is take the limits that recover precisely the systems that Matteo was explaining. For instance, the D2, D6 and the D0, D2, D4. This may be a little bit cumbersome sometimes. For instance, taking the black string limit is actually seems a little bit singular from the real perspective, but one can show quantitatively and prove that you recover exactly the equations and the formula that we maybe showed in the presentation. It was maybe a little bit too much. Okay, so this gives us confidence that this solution is actually, or seems to be correct. It recovers all the previous examples and extends those. So this is great, except for the fact that it's super horribly complicated. So if we want to address any question that we may be interested in, for instance, in this case, the presence or absence of non-perturbative effects, the situation may seem a little bit hopeless. It's very hard to say anything quantitative. However, there's actually a very nice trick that we can use to save us the day and try to relate this complicated system perhaps to a simpler one. And the trick is take advantage of the symplectic symmetries, duality symmetries exhibited by the 4D equals to 2 theory. So as is well known, at the two derivative, there's this symmetry. You can rotate the field strengths and the magnetic duals using some symplectic metrics. This essentially exchanges the equation of motion and the Bianchi identity. This is a simpler generalization, if you wish, of the electromagnetic duality in Maxwell theory. Importantly, these kind of transformations can be encoded completely in how the perpotential transforms, of course, because from here we can derive everything. And crucially, this guy is not a function. So upon performing these transformations, it picks up some extra terms, which depend on the periods, the particular transformation we're using, and so on and so forth. Okay. Now, one very nice thing is that the previous discussion only applies to the two derivative theory, but it can also extend it to the higher derivative one. So including also these BPS terms that Matteo was showing at the beginning. And the relevant transformation law now holds for the generalized perpotential and is exactly the same as the two derivative. So they are exactly the same. from here you can derive how the generalized periods transform and so on and so forth. And the important feature in this problem that simplifies our lives is that, of course, the entropy and any other element observable is a symplectic function, meaning that it's invariant under this kind of transformation. So it doesn't really, the number of microstates of our black hole doesn't really matter how we choose to describe the system, which kind of charges we associate to it, and so on and so forth. And this can be more or less seen by looking at the two pieces that comprise this guy. So the first one is a symplectic product, actually, and the second one can also be argued to be a symplectic invariant. Okay, so this suggests that maybe if we choose wisely a symplectic transformation, we can hope to be able to relate the hard general system to a simpler one. And this is what I'm going to tell you. So in particular, if you choose this kind of transformation that I'm writing, it's not very important. I'm writing it as a symplectic matrix. As you can see, it depends on some parameters, some real parameters, gamma. If you translate this via the attractor equation into how the charges of my black hole will transform, the important thing to notice is that the magnetic charges, for instance, this experience charge is unchanged, but the D0-brane charges actually are shifted. So this suggests that perhaps by choosing wisely these gammas, we can actually gauge away completely the D0-brane charge. And it is well known that a system with no D0-brane charge is actually simpler to solve. And another crucial thing about this particular transformation that I'm choosing is that it's actually a symmetry. It's a symplectic symmetry, meaning that if you insert this transformation into the transformation law of the prepotential, the functional form of this guy is actually preserved, meaning that my new function in terms of my new rescale variables can be obtained by simply taking the original function and inserting the transform, the prime coordinates. And this means that the theory will be left unchanged, the attractor equations will be left unchanged, and therefore the entropy will be left unchanged. So it seems that with this particular symmetry, we can really relate to a priori seemingly different black holes whose charges are linked via this kind of transformation. Okay? And as I was saying, actually the system that will be useful is the D0, D2, D6. So these charges are arbitrary, but now we don't have D0-brane charge. We can cancel out, if you wish, with the gammas. And let me show you that two things. First one, that it's actually simpler, so you can do the attractor equations, do the algebra and so on, and actually you find a much simpler expression. It's very similar to the D2, D6. I think Matteo didn't show it, but it's very similar to the D2, D6. It's actually implicit, but somewhat tractable. And second, if one actually uses this transformation and selects this gamma to be, let's say, P prime, one can show, I don't know why gets frozen sometimes. Oh, nice. So one can show that you recover exactly the attractor equations and the exact entropy, ugly, super complicated entropy formula of the general black. Okay, so this really means that whatever question we want to ask to the general system, we can essentially ask it to an equivalent one with the same alpha parameter, with the same phase and so on, but with no D0-brane charge, and therefore simpler to attack. Okay. So putting everything together, let's look at this entropy formula, and let's try to see whether non-perturbative corrections will enter or not. So there are two places where they can enter. First, explicitly through this kind of imaginary part of the G function, the one that we were computing and playing with a lot before. And there's also an implicit dependence to the attractor equations on the imaginary part of the derivative of G. You can actually compute those, and they look like this. They are exponentially damped with respect to the real part. They also exhibit some oscillatory behavior. And the important point, even though it's of course not non-trivial from this point of view, is that in principle this will not cancel. So they will indeed give some non-trivial corrections to the entropy and in general other black hole observable. So it turns out that actually the D0, D2, D4, the black string, and the D2, D6 black holes that Matteo was explaining before are the exception rather than the rule. So in general, the most general black holes, the Calabi black holes of large volume, will exhibit this kind of non-perturbative effects due to these zero branes. Okay? And the question now is, can we make sense out of it? Can we get a feeling of why? What makes these two systems special? And so on. And this is what the remainder of the talk will consist of. Okay. So of course there are many ways in which you can try to attack this interpretation problem, if you wish. But the approach that we will take here is to to adopt a semi-classical perspective. So what we want to understand now is, let's take the most general two-derivative BPS black hole background and study how D0-brane probe particles, or in general BPS probe particles, behave in this background, semi-classically. Okay. And in particular, we will study that behavior in the near horizon region. The reason will become clear in a moment, but essentially you can think of it as saying that in the near horizon region, the semi-classics can sometimes give us non-trivial information about quantum tunneling, pair production, background instabilities, and so on and so forth. Okay. So in order to characterize this background, let's take the near horizon limit of any such BPS black hole. As it is well known, it exhibits this kind of Bertotti-Robinson spacetime form. So the horizon now is located at y = 0, and RH denotes the size of the black hole horizon itself. Now, as I was saying, this is an ADS2 versus 2 topology, and you can see it very clearly by switching to Poincare-like coordinates. From this perspective, it becomes clear this is the ADS2 factor, and this is an S2 of size precisely given by RH. The RH actually fixes both sides at the same time. And in particular, RH, it's nothing at the two-derivative level, is nothing but the central charge of the black hole stabilized, so evaluated at the attractor locus. Okay, so in particular, it depends on the attractor, on the compensator field like this. Good. So this gives us half of the information that we need. The other half is, well, what happens with the gauge background, right? In principle, my black hole has both magnetic and electric charges that we denote by P prime and Q prime. And this will turn on some non-trivial gauge background both for the gauge fields and the magnetic. Okay. You can actually solve for this background. It's completely fixed in terms of the complex rescale moduli that are fixed, that enter actually the attractor mechanism. And each of these guys essentially has two pieces. One is proportional to the volume form of ADS2, and the other is proportional to the volume form of S2. The details are not important. What is important is what happens if we use everything, we put all this together and we try to study how BPS particles see this background. So the dynamics is captured by the Warland action, as usual, at the classical level. In the bosonic sector, you have two pieces. One is the kinematic piece. It's the usual one. Here, the mass you see, it's because we're taking BPS particles, it's controlled by the central charge of the particle, which depends both on the electric and magnetic charges of the particle. And there's also a gauge cap. In principle, since my particle is ionic, it will see both of them at the same time, right? Now, we can be even more precise and substitute the background that our black hole turns on in the near horizon region. And it turns out after doing so, we get two very simple pieces. We get one electric-like coupling only in ADS2, which depends on some effective electric charge or electric field, QE. And there's also another magnetic coupling in the sphere, which is that of a monopole located at the center of the sphere with charge QM, effective magnetic charge QM. And these two charges, remarkably, or rather not surprisingly, are not independent from each other. Okay, they are completely fixed if you substitute all these background fields and so on by the real part and the imaginary parts of the rescaled central charge of the particle. Okay, and this apparent naive observation actually tells us that the charges satisfy this kind of quadratic relation. Okay, so the sum of their squares is completely fixed to be essentially the mass of the particle in units of ADS. Good. Great. So what about the precise trajectories? What do the particles do in this kind of? Well, it turns out that the system is very symmetric. Of course, it inherits the isometries of the background itself. So it exhibits this SL2R, this is the conformal group of ADS2, and the SU2, the rotational symmetries of the sphere. And actually, this allows us to solve completely algebraically the problem. So in particular, the Warland Hamiltonian is essentially the sum of Casimirs on the sphere and the ADS2, plus some extra shift factor that is actually due to the constraint is essentially the mass. And if you impose the on-cell condition, so the Hamiltonian constraint, namely the fact that the Hamiltonian has to be equal to the mass square, you essentially find that everything is characterized by this formula here. So our two Casimirs have to be equal to each other but opposite inside. So this essentially determines everything that we need to know. But maybe it's a little bit abstract, so let's try to get a qualitative understanding of what our particles are doing. And to do that, what we can do is first solve the sphere problem. Essentially, it's very simple, it's very well known. Your particle is going to precess in one circle around the generalized angular momentum, so the one that is entering actually in the Casimir. This is a free vector of quantized quantities, and this motion is characterized by some angular momentum. My particle is spinning here. So if you could substitute this motion in the Hamiltonian constraint and use some other conservation laws, you find out that there's a radial equation for the radial direction in ADS2, that it's of the usual form. So you have the momentum and some effective potential that depends on the mass of the particle in units of ADS radius, the angular momentum of the particle in the sphere, the conserved energy of my particle, and also the electric charge. But despite all this structure, actually, to understand qualitatively what my particle is doing, we only need to focus or specify the relative size between the electric charge and the mass. Let me explain you why. So in the right-hand side, what I'm showing is literally this potential, okay? I'm plotting the potential depending on this relative size. As you can see, there are two branches, the yellow and the blue. Essentially, this depends on the relative sign of the energy and the charge. You can think of it as switching between particle and antiparticle. It's not really important. The important thing is that you have three possibilities. Your charge can be smaller than the mass. This corresponds to a subextremal situation. Here, my particles come from the Poincare relation, if you wish, from infinity.
Alberto, sorry
Yeah.
to interrupt. You got like 5 more minutes.
Yeah, perfect. I'm almost finished. So great. Yeah, thank you. So my particles come from infinity and are never able to reach the ADS2 one. Okay, they always bounce back. And in depicting the intrinsic trajectory, you see essentially that the particle comes, it's never able to exceed the Poincare horizon, and then it's bounced back. Okay, regardless of which branch I choose. Now, in the super extremal case, or when my charge is greater than the mass, I have two interesting possibilities. This is one of the most interesting cases. If I focus on the yellow one, my particles, again, come from infinity, they bounce back, they're not able to reach the boundary. But you see that there's also another region, which is classically allowed, where I send a particle from the boundary, it bounces back and it's reabsorbed. And this corresponds to the situation intrinsic coordinates that is shown in here. So my particle, the particle is not, doesn't reach the boundary, but there's also another branch. And actually, quantum tunneling between these two is what corresponds to Swinger per production. So the processes that actually discharge my black hole once I switch to the Euclidean perspective. Okay, the other branch, the blue one, it doesn't exhibit these two pieces, but nevertheless, there's also always one particle that is able to reach the boundary. In this case, you see that it comes from infinity and it can go. It's not prevented classically from exiting, let's say, the infinite throat of the black hole. And this is what we're showing here. Okay, these are the ones that are responsible for creating or giving some imaginary part to the Lagrangian, and therefore destabilizing the solution. Finally, there's an extra interesting possibility, which happens when my charge is equal to the mass. Okay, this is the extremal case. My particle is actually able to reach the boundary, but it does so at rest. So it's completely tangent. The trajectory is completely tangent. This is nothing but a manifestation of the fact that in this case, if I take my particle out of the black hole, the two are mutually extremal. They're mutually BPS, so they feel no force. Okay, but they're able to actually go into the boundary, and there's a semi-classical saddle with non-trivial action. But actually, the contribution that it gives at the end of the day, as recently also stressed by Gary, Pushing, and Alessandro, to the action is zero. Okay, in this case, you may have non-trivial, non-perturbative corrections, but at the end of the day, they are zero. Good. So what does all this have to do with our original problem? Well, the point is that from the quadratic perspective, you really see that your BPS particles can never be super extreme. This is great, because this is essentially at the heart of why the black hole solutions, and more precisely, the ADS2 crosses 2 maximally supersymmetric solution, from the semi-classical perspective, is non-perturbatively stable. Particles cannot escape the throat. And this is something that actually you can even check at the full quantum level. But the fact that there are no super extremal particles, and therefore that there's no imaginary contribution, doesn't explain why we find actually non-perturbative real corrections to the free energy. And actually, from the semi-classical perspective, this is very hard to argue. This is something that is still work in progress. We don't know. I mean, there must be something that, from the semi-classical perspective, captures this kind of non-perturbative corrections, but from the usual approach of real saddles in Euclidean signature, this is not seen. Okay. But what I can tell you is that if you solve the full quantum problem, so if you integrate out a particle, BPS particle, in ADS2 crosses 2, so like Gopakumara-Maffa computation, but restricted to this particle, you can solve it. We have done so, and you recover exactly the behavior that we were showing both in Matteo's part and in here. So you find corrections where they should be, with the same exponential damping controlled by the electric charge. This is something that I didn't say, but the damping was controlled when you translate it in this case, the electric charge, and the oscillatory behavior is controlled by the magnetic charge, and so on and so forth. And we also see the cases where shouldn't be those corrections, they are still not there. But despite not being able to say anything interesting, or at least conclusive, from this semi-classical perspective, what we can really say or explain is why these two systems are special. They actually correspond to the purely electric or purely magnetic background. So our D0-brane in this ADS2 crosses 2 near horizon geometry sees the black hole, for instance, the black string, as purely electric and therefore streamal. This means that there's actually an instanton with non-trivial action, but the correction is exactly 0, precisely due to the one loop fluctuations around the instanton. So this explains why, we were seeing these kind of corrections to the prepotential, but they don't enter at all into the observable. And on the other hand, the D2-D6 is purely magnetic. And this is something, again, that we were kind of guessing in the first paper just by looking at the resurgent structure of the prepotential. So the two seem like the electromagnetic analog of self-dual QED, where you have a purely electric and a purely magnetic background. This makes quantitative and precise that observation. Our D0-brane in this D2-D6 system is purely magnetic, and it is well known from old Swinger computation. Purely magnetic backgrounds don't lead to non-perturbative. Okay. So with this, I have hopefully completed the wish list, at least so far. And since I'm probably out of time, let me just leave here the list of topics, of interesting topics, and thank you for your attention.